Okay, so I see that people are coming, nearby about 10 students. So for those who are not used with this tool, in fact, you can ask the question in the discussion part. Normally, you can change the language if you want. There are several languages available. Here is in French, but you can put on your own computer the language you prefer. And then on the chat area, there is a public part if you want to ask a question to Professor Benmokrane, or in the options part you can discuss in private between together. So we are going maybe to wait 1 or 2 minutes more. We have it's 2 minutes to 5, so we have a little bit time. I'm very pleased today to welcome Brahim. It's the second time, that Brahim accepts to participate to this kind of webinar. All those webinars are very open, and generally they are free and available for replay also, and well used by everybody. So it's I'm very glad about this, and it works quite well. So before we are, maybe Brahim, you can hear me quite.
Yeah.
Okay, perfect. So I will introduce you, and then I think we're going to start.
That's fine. Yeah. Mm-hmm.
So well, there is already a lot of people. That's nice. So Professor Brahim Benmokrane is a well-known professor in the field of FRP materials since many years. He is well established in the field of FRP durability, and very used with mainly FRP used as a rebar in concrete, a very developed technology in North America, but start also to be used in Europe. We have several examples of this using in reinforced concrete structures. And the durability issue is always a very important problem that we want to focus on in the civil engineering field. So thanks again, Brahim, for participated to this IIFC webinars. And so I'll let you introduce your topic and maybe give some additional information about yourself and your research. Thanks again, Brahim.
Okay, thank you, Emmanuel, for this introduction, and welcome to everyone to this IIFC webinar. I am talking to you from Sherbrooke in Quebec, Canada. It's 11 a.m. So good morning to everyone. So my talk today will be on durability issues of FRP for civil infrastructure. Of course, I will be talking about internal and also talking a little bit about the external reinforcement. And as Emmanuel mentioned, it's really a hot topic, and of course, this issue has to be addressed through research in lab and also in the field. So as you can see in this first slide, I am from University of Sherbrooke, and I am holding a Canada Research Chair in Advanced Composite Material for Civil Structures, so dealing with FRP. And this is since 2009, and also I have ANSERC, Industrial Research Chair on FRP reinforcement for concrete. This is mainly involving Canadian and also US industry, and also some other partners, some public partners like us, Ministries of Transportation, Hydro-Quebec, and so on, and working on the topic of internal reinforcement. And also I am, from 2010, I am director of the Quebec Research Center on Concrete Infrastructure anyway, so as you can see, I have many things to do. Briefly, my university education, I graduated in 79 in civil engineering from École Polytechnique Fédérale de Lausanne, so it's in Switzerland. Then after 4 years as a consulting engineer in Lausanne, I moved to Quebec, Canada in 82, at University of Sherbrooke, and I completed my master in '83 and then my PhD in '86 at the same university. And from '92, I am as associate. I was hired as associate professor, and as you can see here, just when I talked to you, I was mainly here. If you can see to this. From 95 to 2009, I think some of you know that we had here in Canada a research network of research center dealing with called ISIS Canada, and it was really the impact of this center was really huge here in Canada in North America. So during 14 years, we worked in this field of FRP. Internal, external, and also we worked about structures monitoring using fiber optic sensors and something like that. So this is really, it was, I can tell you, a huge achievement were made through this network of centers, and many about development of codes, design guides, and so on. And still now, and still the Canadian industry and also North American, and I can say also the world industry really still benefiting from the finding of this Canadian Research Network of Center of Excellence. Briefly here, in terms of Canadian standards dealing with FRP, as you can see here, I am the chair of the technical committee CSA S807. This is dealing with the specification for internal reinforcement since 2008, and we produced the first standard in the world dealing with the qualification of FRP rebar. And also since 2002, I am the chair of new technical committee CSA S808. This is equivalent to S807, but it's dealing with external reinforcement. And also in 2014, I will talk on that a little bit later. We produced also a new standard dealing with the external reinforcement and how to characterize this material, like as for short-term properties and also long-term properties. I will show you some slides dealing with these two standards. And also I am the co-chair of the technical committee CSA S802. This is really dealing with the using of FRP for buildings. And we just, in fact, 2 years ago in 2012, we published the new edition S806 2000. Here there is a mistake. This should be 806. We published in 2012 the new edition of this code. And also I am the co-chair of the technical committee S16. This is dealing with the use of internal and external reinforcement for bridge components. And we just come out with one new edition also dealing with the Canadian Highway Bridge Design Code. So if some of you would like to have more information regarding the standards, please feel free to contact me. Also, in terms of the research activities here in my research group, currently I have 4 master students and 14 PhD students, 5 postdoctoral researchers, 2 technicians, and 1 technical assistant. And this is all this person are working mainly at 95% on internal reinforcement. During the last 4 years, 11, almost 20 graduate students completed their studies under my supervision. You can see here also about the technical papers that we published together with the student and postdoctoral during the last 4 years. About research funding, this is what I have, mainly from the Canadian and also from the Quebec government and also from the industry. And as you can see here, I'm doing really research work not only at the national level, but also globally at the international level, also working with the USA, Australia, some countries in Europe, and so on, particularly on internal reinforcement. Also briefly, this is about the research activities, one of the main topics that we are addressing here in Sherbrooke is about the viability of FRP reinforcement. I can tell you we have, I think, one of the largest research facilities in North America and maybe also in the world. And we are doing extensive laboratory investigation on glass, carbon, and basalt. We just started a new research project with the Florida DOT dealing with degradation mechanism of GFRP rebars and also CFCC Tokyo rope cables. So we are working on that now with some colleagues from US. Also, we are addressing other topic with the long-term behavior. This is one of the topics that we'll be talking later about correlating lab aging tests compared to the field, as you will see later, and also developing service life prediction. As you know now, most of the Canadian national and international codes are specifying service life 75 up to 150 years for the civil structures, and of course we have to demonstrate that the FRP will at least last this duration. And this is the way that we can do that is, of course, by developing prediction model, and all these findings are being introduced in national and also in the international code and standard, as I mentioned. And all this durability test also is helping for specification for product certification as internal and also external reinforcement. Briefly, before going to the main topic of today, I wanted only to show you some project that they already completed, or some of them they are ongoing. You can see here about the, of course, I will be coming back to the durability issue and material issue. So here I will be showing the next slides mainly about the structural testing. This is, you can see one of the view of the old structural labs that we have. It has strong floor 10 meters by 20 meters. You can see here, this is one full-scale underground chamber under test. We can see here in the back shear wall. We can see here one bridge pier under testing, and so on. So this is, we have many graduate students using it. And also we, in 2009, we had a new structural lab, which has strong floor 12 meters by 20 meters. We have MTS machine 16 meganewton, and as you can see here, some L-shaped reaction wall 12 meters. And I used this walls mainly for testing shear walls. And I am planning really in the future to test here one building having 4 floors, which include all slab, beams, columns, internally reinforced with FRP, and looking about its behavior under gravity load and also under lateral load, mainly for seismic. So this is all these structures really lab are graduate students are taking benefit from that. Here's some of the specimen. We can see here FRP reinforced slabs, deck one-way slabs and two-way slabs that we tested during the last few years. This is two-way flat slab for parking garages. This is two-way slabs for bridges. You can see here we put the flexure reinforcement and also shear reinforcement were made with FRP, as you can see here in this photo. Also, we tested circular beams. This is mainly for pile application. This is under flexure and under shear. You can see here the internal reinforcement, the cages. Also, we, as I said before, we tested shear walls. This is mainly to look about the seismic behavior. This is mainly for the building application. We just also recently, in fact 2 weeks ago, we completed testing also columns. This is all reinforced with GFRP, and this is under quasi-static loading and looking about drift and energy absorption and so on. And we got really very, very interesting results. Some of the columns even went up to 8% of drift without any strength decrease, which is really very good behavior. We look to the behavior with different longitudinal reinforcement and also with different lateral reinforcement for the concrete confinement. Also, this is another view showing shear strength evaluation, T-beam section size effect here. This is to have 1.2 or 1.4 meter depth. And this is also about the deep beam also that we tested with one PhD student. Here also we did also extensive work on torsion. We looked to that about this type of loading, and it happens often in bridges and also in parking garages to have this kind of load about torsion. Also we tested columns, rectangular section, circular section, short columns, slender columns, with glass, with carbon, under concentric loading and also under eccentric loading. We are now establishing the moment load diagram interaction. We have really huge work on that, and this is mainly for code development and so on. And also we tested, as you can see here, this is bridge component, including body walls. As you can see here, this is under static load in the lab, and here under impact load in the field. And also this is under crash test we did that in Texas, also as exactly how it has to be tested as you need to approve the material. Sometimes also we are bringing precast full structures as for testing. As you can see here, the chamber, the transportation to the lab, this is during casting, and they were tested recently here in the lab. Also, of course, we are from the lab, all structural testing that I just show you. Some of them, it really helped for developing new applications with GFRP reinforcement. And of course, we move it to field applications. We have to do that, as you know, because we can know more on the material and we can increase the extension of the use of this kind of material. See here, I can show you a couple of bridges. You have one span bridge. You can have a continuous span bridge in casting place concrete, as you can see here, or with precast element. Here, myself, I was involved for at least 15-20 pilot projects instrumented with fiber optic sensors. But in Canada, we have more than now 400, we can say, bridges where GFRP were used in the deck slabs. You can see here also another example of parking garages. This is demolition of the existing structural slab and replacing them with new slabs with GFRP. This is one-way slab. And also we did with two-way slabs, parking garage. This is having the span of each bay, it's 30 feet, which is 10 meter length, which is really very, very long. We had some it was really challenge mainly about the deflection here, the behavior, and also about the punching shear behavior around the columns. But we addressed that very well with the designers, and all this are instrumented, and we know exactly about the behavior. Also, concrete tank. This is also very good application. This is mainly for chlorination for water treatment plant. As you can see here, this is the slab on floor, the foundation, all with the GFRP. You can see here the wall and the casting here, the cover slab, and you can see here all the structure completed. And this is all what was made with GFRP. And I think now there are 2 or 3 of this kind of structures here in Quebec and also around the world. We have also on highway. This is continuous concrete pavement in highways in Montreal and also other cities. One bridge that on which I worked during the last 2 years. This bridge is now under construction. It's really the first time in the world to use GFRP in cable stayed bridge. As you can see here, this is 2-span bridge. It have more than 250 meters. You can see here the 3 towers. and all the slab was reinforced with GFRP. As you can see here, it will be with jointed with the ductile for this one, and you can see here the precast slab. It was also challenged, as you know, to design that because, as you know, with the cable steel, we have a huge compressive forces mainly close to the tower, but we worked with the moment load diagram, and we went to a very good design. As you can see here, we produced calculation note to the designer consultation engineering firm in Toronto. The whole bridge also it's being instrumented with fiber optic sensors, and it will be open to the traffic by end of 2016, and we'll be doing some live load tests also on this kind of bridge. Also, there are incinerator. This is also one-way slab that we did also like asphalt application. You have also like as reinforced concrete soft eyes, as you can see here. This is in subway in North Tunnel in Toronto. We did that last year, and it was really a huge project with that. And it was also a challenge to design for shear particularly. Also some other project at the international level. This is in Miami, returning wall. This is the new port of Miami tunnel project. I did that with the French company Brahim, and this was really the first time that I implemented pass-out bars, as you can see here in these two walls. And so if you go to Miami, you can visit it. We built some slabs, and we'll be taking cores from the wall and also from the slab, and looking about the long-term behavior. Also one project in Morocco. This is in Tanger to the this is you can see here the GT. It's really beautiful area, as you can see here. And all the GT that we're having here, this is the boxes, 95 reinforced concrete boxes. You can see here the huge quantity of concrete that it was used. And you can see here also the basalt bars that we used to reinforce the top of this boxes. So also this I did that with some international partners. So it gives you an overview about some project that we completed in the lab and also in the field. And as you can see, I think this the FRP rebar technology, it's really well progressing, and now it's really being used at the international level, and I am very, very happy about that. So after this, we can say brief introduction. It's about 10 minutes. I'm sorry about that, and I hope that it was very helpful for you. So the outline of my presentation today, after a brief introduction, I will talk about the factors affecting the derivative of FRPs. I will talk about accelerating aging tests. This is the way how we have to do derivative tests in the lab. Also, I will be talking about ISIS field derivative studies. This is it was really a huge progress made with this field testing. As you know, you will see that about later, and the acceptance about the material and so on. Specification codes and design guides, how we are addressing the durability in the codes and design guides, and some concluding remark, and I will come out with some research avenues. So the first thing that we have to understand when we are looking to the derivative of this material is trying to look about how this material is made. As you can see here, the FRP has, we can say, three main components. We can see here the fibers, the resin, and the interface. So any degradation or any interaction will be mainly around the three components, and all of the three have to be, of course, addressed. And if one of them is not really, you can say, not durable, so the whole system will fail, of course. And this is why it's really extremely important when investigating is really understanding the whole behavior, including the three main components. Why is derivative concern? Of course, because FRP is still new materials when we compare it to traditional structural materials. Also, the manufacturers are still also doing innovation, so they are coming with an example, using new products or coming with new materials. So they have to be evaluated and understanding and looking to their long-term durability. And as I told you now, currently most of the code, they are specifying 75 or even more than 75. And of course, the durability of this project has to be proven that at least it will last the service life in the code. Also, yeah, this is unlike steel. Of course, FRP are resistant to electrochemical corrosion because it's non-metallic. But however, FRP could potentially deteriorate following exposure to some specific environment. We can see here physical, loading, moisture. This is really the main critical issue because without moisture, the durability will be I think no problem at all. Temperature also it could affect depending if we are talking about the fire or in some application in Middle East. Chemical, of course, mainly with concrete. So we are here talking about alkaline solution, but it could be also another chemical. And the rate of deterioration, as I explained it before, it will depend on the type and type of fibers, the resin matrix, the fiber matrix interface. This is, I can tell you an example now. I am working on basalt bars during the last few years, and now one of the main issue about long-term durability of basalt is really dealing with the fiber matrix interface, because until I can see the industry, it's still facing to the problem with the sizing and finding material which has really good compatibility with the resin. So it's still really under research and one of the key issues to be addressed in the coming years. Manufacturing process, mainly about rate of curing and void content. I will show you some slides later about that. And the exposed environment depending on application, as I said before. Sometimes you can have freestyle, in some other case you can have marine application or so on. So it has to be addressed. About degradation process, we know them very well. We know that FRP material could degrade by fiber. As you can see here, cracks in the fibers. It could degrade by the matrix. As you can see here, you can have cracks, micro cracks in the resin, or it can be chemical degradation. Of course, in the resin, we know very, very well about that. And the interface dominated, as you can see here, we have some debonding and delamination. And when you have this debonding and delamination, of course, you are losing one of the main criteria, if you can call it in this way, like to act like as composite material, because when you are losing the interface to the whole material of the whole system is not really acting like as composite, and you can have decrease in the strength, and because you don't have any stress transfer between the fibers. So we know exactly how the material is degraded, but we can say we know a little bit less about the interaction, because we can have the interaction or synergic effect. As you know, we can, by combining load and chemical, we can have some synergic effect. And this is, we don't really know really too much. And from a point of view, it needs some study by having the synergetic effect, by combining load, temperature, moisture, and so on. I can see it in the future to look to this kind of behavior. Of course, as I say, this material is, we can say, is really controlled by the microstructure, which is controlled by the choice of the constituent material, the interface. I'm repeating this, and also the manufacturing process. The manufacturing process, I can say, it was really a huge issue. We can say maybe 15 years ago, 20 years ago, when people they were starting, as you know, and understood developing this kind, there were really problems with that. I remember when I looked to this material by the end of the 80s, beginning of the 90s, and the product really, it was not really very well now manufactured. But now the manufacturers, they have their own quality control and using advanced machine and also advanced materials and doing that really properly. And now also, of course, with the specification and the certification, they have to do a very good product. Otherwise, they will not pass the qualification as specified in the standard and code. So we can say this is really well controlled, which is really good news. Scanning electron microscopy, this is really an excellent tool, as you know, of course, to investigate the microstructure of this material, and mainly looking about the interface. As you can see here, we have really good fibers and well distribution. We have also, as you can see, this is longitudinal section, and this is cross section. This is really good, very good bonding, and there is no free gap or something like that. And this is one of the bars, combar, I think it's from Shock, that I did this investigation. And this is, it was done, I can come back with the manufacturing process. If you look to the rebar, there are mainly two manufacturing process. The two are made with pultrusion, but there are some manufacturing using closed die pultrusion, and some other they are using open die pultrusion. So when you are using closed die pultrusion, you don't have access to the bar, as you know, during the fabrication. So it's not really in contact with the atmosphere, and in general there is no void, and as I show it with the Shock. Sometimes, but this is for the external surface. You have to add sand, or you have to do grooves or something like that after you made the smooth bars. But when you are using pultrusion with open die, this is, of course, you have access to the rebar during the manufacturing process, and this is, you can add helical fibers, or you can do any external deformation, as you know, before the resin, before the polymerization of the resin. But as you have access, so it means that is in contact with the atmosphere, so you can have some pores and something like that. So the thing is to have well-distributed pores, as I will show you later. So this is really extremely important. Next one, of course, this is for, as you can see here, this is pore bonding. You can see here the gap. And this is, of course, this is before starting the investigation. And I strongly really recommend to you, when you are doing durability investigation, do also microstructural analysis on the material as received before conditioning, because sometimes you can find a lot of defects and problems from in the material as received. But if you will not do it, and you will start your investigation, and maybe you can come up with some wrong conclusion, because maybe the deterioration it was in the existing, in the as received material. It was not really induced by the load or by the environment. So I will strongly encourage you, when we are doing that, you have to do that really also on as received material, looking about the microstructure and if there is any defect or not. Also about the interface characterization, this is, you can do it before testing and also after testing, like on fractured area, and this is give you a very good idea about how about the interface. As you can see here on the left, you can see here this is on fractured area, and you can see here the resin, it's still bonded to the fibers, which is meaning really good, very good interface, and showing the integrity of the interface. But as you can see here on the right, you can see smooth fibers, and all the resin was removed because it was mainly the failure, it was at the interface, which is really poor bonding. So this it will really explain to you. And when we are doing an example for testing basalt, this is kind of the picture that you can have. And when you are testing glass with vinyl ester, an example, this is the kind of picture that you get. Also, when we are testing carbon with epoxy, an example, or even also with mainly with epoxy, it has good compatibility with epoxy, like as carbon fibers. But yeah, this is also one of really what happened in the interface when you have problem with the interface, and this is with basalt bars. As you can see, this is picture coming from one bar sample conditioned in alkaline solution at 60 Celsius during 3 months, and as you can see, the strength reduced by more than 45%, and you can see here the fibers debonding, and it's induced the huge strength decrease. Also, long-term durability could be affected, as I said before, by the porosity gaps, as you can see here, or it can be by fiber impregnation, as you can see here. And this kind of defect, you can find them in as received materials. So you have to look at it as before really starting your testing and studies. Glass transition temperature, this is really a thermal property which is extremely important. We can do that with DSC, or we can do that with DMA. We have STM standard on both methods. But anything, it gives really a very good idea about the long-term stability of the resin, and by having and by investigating the glass transition temperature, we can know really more about the behavior of the resin. Here also I am summarizing the most chemical degradation of the resin. Can be by plasticization, which is reversible. This is mainly by moisture, or you can have it by hydrolysis, and this is of course it's not really reversible, and you will see it by looking to the thermal properties. And of course here, this is extremely important that all good FRP should have completely curved resin system with high glass transition temperature and low moisture absorption. And this is, of course, it apply for factory-made product like as rebar by pultrusion, and also it's applied for external reinforcement for field application. As you know, when it's made by hand layup, also we have to consider this thermal property, of course. This is result from DSC. This is, you have cycle 1 and then cycle 2, and as you know, because we did cycle 1, so we already heated the polymer resin. So this is all showing that there is post polymerization, as you can see here. But when we did the cycle 2, as you know here, it's continuous strain line. So the system was now curved, fully curved, and as you can see, we jumped the TG from 62 to 85 because we did some post polymerization, and it shows that the resin it's linked. And okay, this is my phone. I'm sorry about that. Primary durability in FRP, of course, as I said before, as in when we are using FRP in civil engineering, so we are facing to different kind of environment and different kind of load, as you know. So it can go from moisture, as you know. We cannot avoid the presence of moisture in civil structures. We can have a temperature depending on the application. We can have elevated temperature due to the fire. An example, we can have alkaline attack, and as you can see, there is really a variety of environment. And of course, we have to look mostly all of them. Some could affect more than the other. As we know that an example for internal reinforcement, like as a GFRP, we know that alkaline is one of the critical issue, and we have to look about it before looking to the rest. But as I mentioned to you, please keep in mind about moisture. If the structure of the application with the FRP is we don't have too much moisture, I think everything will be fine with long-term durability. Of course, by addressing this in the lab, we have to generate data for long-term behavior. We cannot build structures and waiting 75 years or 100 years to know if the material is durable or not. So we, in general, during the last few years, the researchers developed what's called by accelerating aging test, and this is mainly by accelerating the degradation by using elevated temperature. But we have to understand here about accelerating aging tests. I can recommend to you. There is one book written by Nielsen. It's really it's an excellent book, and you have to look at it. And it's applying this accelerating and service life prediction for all the product. Even sometimes you can go to Toys R Us for buying something for your kids, and this is also, it was tested under accelerating aging test because we know to know how durable is this material. But of course, we can use it also for our for civil engineering and FRP reinforcement. But there is assumption that degradation is caused primarily by single chemical reaction. This is, otherwise, if you have 2 or 3, of course, you cannot use accelerating aging test. So if the correction is correct, then the rate of reaction can be increased by increasing temperature, and specimens are aged by placing them in solution bath as we are doing. So here, this is, and we believe strongly that our degradation is mainly coming from chemical reaction. It could be from the resin, or mainly from the interface, or it could be from the fiber, as I explained before. And of course, we can see it when we'll be, I will explain to you later, when we'll be drawing the result and the curves. We can see if this assumption is fulfilled or not. So conditioning here, I'm showing of specimen in temperature and bath. This is all of them. It's not really under load, because if we have load, so we will have the synergetic effect, and it could be also investigated under that. But mostly we are doing that without load. And we are limiting the load, of course, to the minimum for not inducing any other problem. This is what I showed you before, is the bars are, or the FRP are directly immersed in alkaline solution. Sometimes also it could be like, here the bars or FRP are embedded in concrete placement, and we have them in water. So we are directly using the concrete as alkaline, and also here we have it also bar in concrete block, and this is mainly here looking to the long-term bond and if there is any degradation at the interface. Also we can have them under load, as I show you. This is some of the testing here in Sherbrooke that we did during the last few years. We can have, this is, I'm showing you some slides from the research lab that we have here in Sherbrooke. As you can see here, we are also investigating the long-term deflection. These are from 2007, 2008, and this is all loaded under service load, as you can see here, with gravity load from the concrete blocks. Also here we have beams of small size. This is really full-scale beams. And also we have here clip frames under load, different load and so on. We can do them also in beam, as you can see here. This is under freestyle cycles and under sustained load, and then we can look to the long-term behavior of by investigating the deflection behavior and also the capacity of the beams, and also we can extract the bars from the specimens and doing the tensile test. We can do really variety of testing, and mainly about the objective that we are looking. Here the cycle that it was done from plus 20 Celsius to minus 20 Celsius. And this data was really very helpful, as you know, to develop new codes, new standards, and also to convince engineers to use this material with this kind of testing, showing them the performance of the material under such environmental testing. This is also kind of the result that we can achieve. This is about moisture penetration, and as you can see, as function of the temperature, the ambient, you can see it here, 23. 40, 60, and 80. So as you are increasing the temperature, as of course the rate of diffusion is increasing, and also the maximum moisture is increasing, as you can see. This is why the temperature is being used like as accelerating aging, as seen here in this. So it will happen exactly the same thing in the specimen that you will be testing. And we can even find from this curve, we can find really the accelerating factor from the 20 to the 80, or from the 20 to 60. I have a couple of papers on that in AC Journal of Composite that you can look to them. Okay, then after we can also learn tensile test. This is mainly for the strength retention, as you can see here. You can do it here. I'm showing it for rebars, but you can do it also for the external reinforcement, like as for laminate and so on. And then we, from this test results, we have here the tensile strength, and this is an example showing in water. We can also derive the same result from alkaline. This is about the days in conditioning, and we have different temperature: 80, 60, 40, and 23. And as you can see, as we are increasing the temperature, as the strength retention is reduced. And from this we can derive long-term strength. So to use and to derive long-term strength, of course, this is based on Arrhenius relation, as I said before. And here I am reporting one procedure developed by Larry Bank in 2003. Which need 3 temperature of aging and 4 periods of immersion. So here it could be like as 20 ambient, 40, and 60, and here it could be 4 period of immersion, like as 45 days, 3 months, 6 months, and 1 year, an example, or 1,000 hours, 3,000 hours, 5,000 hours, and 7,000 hours, something like that. Yeah. And from this, this is from Larry Bank, we can draw this that kind of curves. And if we look here that all the curves are really parallel, so it means we had only one degradation mechanism, which the Arrhenius will apply. Otherwise, if they are not parallel, so it's that we have some combined or 2 or 3 degradation mechanisms we cannot use Arrhenius. So you have to be really very careful when you are doing this testing, and you have to have this. This should be all parallel as shown here. And from this we can draw the strength retention as function of the time. This is in years, and we can do it with any temperature. Here I draw it with like 50 Celsius and here and 10 degrees Celsius, like as average annual temperature. It doesn't really mean that our material, when it will be in the field, it will be having this way. I think what we observed from the field is the strength will be not as what we tested in the lab, because from the lab, of course, we used very aggressive environment. But it will give really very good idea, and of course it will be convincing the engineer. And we can be also, as you know, very conservative, and this is what we have in our code by specifying the reduction factor that will taking into account such results from the lab. So a couple of years ago, through ISIS Canada, as I mentioned before, in 2004, really we were very interested to know the material that we implemented in different bridges here in Canada. We were really very curious, we can say, to look about how this material now is behaving and what is the state of this material. So we did what's called viability of GFRP as internal reinforcement in 5 in-service field structures. We did that also in 2006 for external reinforcement, of course, and as showing you this, you have it here in the bottom of the slide. I will be focusing mainly on the GFRP because really this study, from the time when we did this study, and it was shown clearly that the GFRP bars was really very well behaving. At the time, we we in the Canadian Highway Bridge Code we introduced the GFRP like as main reinforcement in bridge components, because before it was only like as secondary reinforcement. And this field study was extremely helpful to introduce GFRP like as main reinforcement. This is a photo showing the people who were involved in this 2004 ISIS durability study. You can see here myself and Dr. Nami Banchia, Aftar Mufti, and Mubul Fiza, for all of them from British Columbia, University of Manitoba, and University of Saskatchewan. So what we did, we really took a course from all these 5 bridges, Joffre Bridge here in Sherbrooke, Crouchel Bridge in Alberta, close to Calgary, Halls Harbor, this is in Halifax, Nova Scotia, Waterloo Creek in British Columbia near to Victoria, and Chatham in Ontario. And we did microscopic and physical-chemical analysis and looking to the microscope. So we took course, as you can see here, from all these structures and from 5 demonstration projects. And then you can see here the course, you can see here the bars. We took from the barrier walls, from the sidewalk, and from the slabs, and so on. And we sent them to the 5 universities, and really we performed all the tests. It was performed independently by 3 research teams located in 3 universities: University of Sherbrooke, University of Manitoba, and University of British Columbia, where we did the test, and also Saskatchewan with Mobile Fiza. And then this is the technique that we used in analysis. We looked to the GFRP concrete interface by using optical microscopy, micro-cracking, and physical degradation of the fiber resin and glass and resin interface by SCM analysis, degradation and thermal properties, as you can see, by DSC, chemical degradation of resin by infrared, and concrete structures looking by X-ray degradation. We did also EDX. I'm not showing it here, and many other analyses. And here show some slides showing the optical microscopy as near about the interface. Here showing 3 different structures, and we can see the interface is really anti-mite and no debonding, no micro cracks, and no void in the GFRP. Also, this is about scanning electron microscopy. There is really, and here really I'm showing here some slides, but we did hundreds and hundreds of specimen, and we can say thousands of pictures, and looking to them, and we did not really see any resin microcracking, no glass fiber degradation, or any significant delamination in this material. Also about scanning, DSC, as you know, about we compared you have the reference, as you know, on the right. This is the reference specimen, and this is the in service, and you can see as they are quite similar, and which is showing no signal of degradation of the resin. This is from the infrared spectra of Joffre Bridge, and if you compare this curve to this curve, also the same thing. So they're showing no chemical degradation, which is the hydrolysis from this and this vessels. So from this one, we come up with this conclusion. At that time, the structures, they were having 5 to 8 years of service condition. Of course, it's not too much, but it at least shows something, because I remember at that time in 2004, 2003, we looked to some papers that it was done by some researchers from lab testing, and they were showing that the GFRP, when it's put in the concrete, the degradation is starting immediately. And even some of the papers, I remember, they were published in ACI Structural Journal. They were showing the service life maybe could be 1 year, 2 years, 3 years. But from the accelerating aging test in the lab, so even here it was 5 to 8 years, but without showing any degradation to it. So it was really very encouraging and very positive results. And we decided, as I'm saying here, to really introduce the GFRP as main primary reinforcement in bridge component, but limiting the stress to maximum 25%. And from this time, we did another field durability studies in 2009, so it's bringing the structure to 13 years, and also we have almost the same results as you can see in this next slide. So also we look to the interface as you can see here, and there is no degradation. It's almost the same result as in 2004. This is from SCM analysis, as you can see here, the fibers and also the resin. This is another bridge for Joffer bridge, as you can see here. And it's really very, very positive results. And we are planning maybe to repeat this kind of field study by 2016. So at that time, we will have almost close to 20 years. Which is good, and I can tell you now there are hundreds and hundreds of structures here in Canada and in many other countries using GFRP. And the reason that why people are using GFRP because as you know, it's in terms of cost, because the cost is really the key issue when you are using new material. And of course, GFRP, it has the lower cost compared to carbon, aramid, or any other FRP. So this is the reason why. And now even from the field applications that I showed you before, parking garages, bridges, and many other, we did cost analysis by comparing the same structure reinforced with steel, black steel, or galvanized or epoxy coated bars, compared to GFRP. And almost now, even with we are really not looking to the life cycle cost, but only with the first cost. And even now, the first cost, as I can tell you, is almost the same thing by using GFRP or using other metallic reinforcement like as galvanized or epoxy, something like that. There is no, of course, now most of the North American authorities now they are specifying GFRP and stainless steel, and even now making even GFRP better, because of course it's 3 times, we can say 3 times to 4 times less than the stainless steel rebars, which is really very good news. So from my point of view, the use of GFRP rebars will expand in the coming years, and I know now the industry is coming with improved fibers, with also better resin, and now I'm working with some companies, even they are enhancing their manufacturing process, and mainly to produce the bar a little bit faster, as you know, to be able to produce more bars per hour, an example, so they can also maybe also reduce the cost during the manufacturing process, because the cost of the manufacturing process, we can say it at least around, depending, but it could vary from 50 to 60% of the total cost. So if you can work on that, I think we can make even this product more competitive compared to the other reinforcement. So now I will talk about some material specifications we have here in North America. I know also I think in Europe also they are doing the same thing. Here, as I say, we come out in 2010 with the specification for internal reinforcement for rebar, and in 2014, last year, we come out with external reinforcement, and also we have it in the ACI in 2008 with the internal reinforcement, and here this X should be 2013. I'm sorry I did not modify this slide. It's I think it's dated from 2011, 2012. This should be 13 here, and it was developed and it was also, of course, published. And we have the international code, the Council ICC, also on external reinforcement. So about the North American, so this is for the internal reinforcement, this is the Canadian, and it was really at the time the first code in the world of the first standard. Now we are working about internal reinforcement from both sides, Canada and US. We are working, I think we will have it by the next year. It will be STM standard, which will be dealing with the material specification for deformed and sand-coated GFRP bars. The document is, it was balloted, I think, 2 or 3 times, and from a point of view, it will be even maybe ready by the end of the year. And I hope that this international STM standard will be used at the international or globally. I think this will be fine, because to have something which is used all around the world. So I am being involved in this STM mainly with my colleague Charles Beckes and Russell Gentry, who are the chair and the co-chair of this STM. Also, we have it, as I say, with external reinforcement. This is the Canadian one that we. This is also really one, I think, the first standard in the world. I know Emmanuel Ferrier, he's a member of this technical committee, and we come out with that in 2014. And the equivalent one of the ACI is in 2013. I will show you some slides about this standards later. So if I will start with the S807, I will show you only some clauses dealing with the durability. So about the scope of this standard is really dealing with the internal reinforcement, and we are talking with non-pre-stressed internal reinforcement. So mainly about FRP bars or grid, and which is used for bridges, building, and marine structures. So we are fixing really about the manufacturing process, about the material, about the qualification, about everything. So any manufacturer to have its product or their product to be approved by any governmental authority or by any private organization, they have to go through the qualification and showing that their product is really fulfilling all the criteria in the standard. Otherwise, it will not be approved and not be used. And this is, I think, it's very good for both the engineers and users, and also it's very good for the industry, for the FRP industry, because if we allow, if we don't have the standard, and any industry could manufacturing bars, as you know, I think we can have huge problems and can have catastrophic failures, and everything will die very quickly about all what we did during all this 20-25 years could be lost in 1 minute. So we have the physical and durability properties. As you know, all this kind of properties, they have to be evaluated. And mainly here you can say about alkali resistance in high pH solution. We have void content, curve ratio, as I talked before, water absorption, and creep and fatigue also has to be done. I don't really want you to go through all this. I put it only to show you that we have here the property here. You have it here on the left, and then you have the qualification test. We are specifying the number of tests and so on. Here we have the manufacturer quality control, how many tests they have to do. The owner quality assurance, this is for field application, and there are also something that it could be provided as a request. And here we have the test method, specifying the test method. And here we have the specified limits. So we are giving a number. So this is how it works. So property, qualification test, manufacturing quality control, quality assurance, provided as request if it's not in industry, and then test method and specified limits. So we have them for all fiber content, water absorption, glass resistance, temperature, and so on. And this is all. We have the number of tests, the number of lots, and so on to be tested, etc. As you can see here. So there is no need. And this is a summary that we have durability-related provision. We have limit on diluent and certain fillers, limit on low-profile additive. This is mainly manufacturers are using that to control shrinkage and so on. Non-blended resin, we are not allowing to have 2 types of resin. It has to be the same type and the same category. Lower limit on glass temperature and cure time. We are specifying minimum cure ratio and minimum glass temperature. and material screening through physical and durability, void, water, and so on. Many properties, as you can see here in these slides. This is an example from the limits that we have from the S807, water content, void content less than 1%. And this is really very good. I can tell you most now about the internal reinforcement, about the bars. All of them, I can tell you, as I explained before, if it's made by pulverization open die, in general they are getting 0.5, 0.6. But it's by closed die, sometimes they're getting 0.1, 0.2%, because as I told you, there is no contact with the atmosphere, and there is less than, the void content is really less, and also taking care about the speed and about everything for not creating any cracking from thermal stresses and so on. Water absorption less than 0.75%. Most of them, they are getting, of course, this is really, I'm telling you, for the internal reinforcement. You will see later when we are talking about external reinforcement, we don't have at all the same numbers, because the manufacturing process is not at the same. But we are having more, as you know, lower value with the free factor and so on. Anyway, water absorption curve ratio, glassage temperature, and alkali resistance greater than 80%, 70%. Maybe some of you will ask from where they coming this number. As in, when we started developing this standard, we based our analysis on the durability study that we did from the field. At that time, we were using mainly three products, one from Pultral, one from Hughes Brothers, and another from Marshall Industries. Most of the bridges in Canada, about with the rebar, we used these three bars, and we generated huge data in alkaline solution, without load, with load. We did really hundreds of testing here in Sherbrooke and also in some other universities. And from this statistical analysis, based on the three products that we proven to be really durable in the field, so we come out with this 80, 70, and so on. Maybe in the new edition, because now all the bars that they were qualified and they were tested, I think at least I know at least 5, 6 that they went through the whole process. And most of them, they are getting, of course, higher number, greater than 90%. So maybe we'll come out with a new number in the coming edition that we'll be preparing by this year for the 807. Okay. Next one is, another topic that I wanted really to talk. This is a new slide that I introduced about the fire resistance. As you know, we have here in the Canadian code the S806 for the fire resistance. I'm talking about internal reinforcement. We addressed that really by using some charts. We have them in Annex O in S806, and we addressed that only with the concrete cover. And it was mainly derived from finite element analysis and theoretical analysis. So we used the time rating that we have here for building by the Canadian building code is 2 hours for building. But we were not having any test results. So when we developed the S806 code in 2012, I was really one of the responsible of this of clauses regarding the fire resistance, because when I show you a couple of parking garages, and when we did this parking garages, we specify a concrete cover of 60 millimeter, and at that time we say we'll hopefully that in the future we can do some tests and maybe this concrete cover could be revised. So we did testing last year, and as you can see here, this is 2 slabs. Reinforced with the FRP. They were really designed like a slab for parking garages in terms of stress on their service load. I will show you before. I'll show you later. This testing, I did that in collaboration with Mark Green from Queen's University, who is really one of the international expert in this area. You can see him here in the front. This is Mark Green. So this is in one of the lab that we have in Sherbrooke. So the slab we did with two products, one GFRP bar sand coated from Pultral and one from deformed bar from BP Composite in Alberta. It's really the same thing, the same reinforcement, bar 16 millimeters space at the 150. The span of the slab is 3.8 meter. As you can see here, this is in the Fire Research Lab in Ottawa. This is really, it's a recognized lab and being used by all the Canadian industry and also by the government. This is the only one. This is the only lab available for the fire research testing in Canada. You can see here the two slabs. This is slab placed on the floor of the furnace. Picture, of course, taken from the inside. You can see the flames will come from this. Of course, let me to come back here. When we cast the concrete, we kept it in the lab during 6 months to get the moisture out of the concrete, and then we transported them from Sherbrooke to Ottawa. It's about 350 kilometers, and then we put them in the test setup in the furnace, and you can see here this is what we did the test according to the fire test according to the CSA Canadian ULCS 10107, and this is exactly the same as the STM E119, and it's only on fire test, and the test was done on 25. I can tell you at that time I was extremely stressed because can you imagine, depending how much time the slab will last, it could have a big effect, as you know, on the whole industry. This is showing the hydraulic jack. This is from the top of the slab, showing the hydraulic jack. As you know, we applied uniformly distributed loading, as exactly it has to be done, and we applied and we generated in the tensile reinforcement in the bottom. It's about 2,800 microstrain, which is really little bit above the service strain expected in the field. So it was really done properly. You can see here some gauges, strain gauges, and also thermocouple. And this is during the fire test. As you know, you can see here, this is the curve of the STM or the standard. As you know, this is the minute, the time. You have it 0 minutes, 50 minutes, 100 minutes, 150, and 200 minutes. And this is how it's increased. As you can see here, the rate, it's increasing. As you can see here, about 700, it was reached in less than 10 minutes. And then increasing and going to almost 1,100. This is what we reached the curve. And this is all the thermocouple, the temperature, and this is depending on the concrete cover. We have the slab. It has I think 230 millimeter thickness, and we have the first one is 180 millimeter from the bottom. And as you can see, it's the lower temperature. As you know, even at the maximum, it reached less than 170 Celsius, as you can see, which well below the glasshouse temperature. And as you are going, like here at 20 millimeter concrete cover, as you know, we have this one, which the temperature is really very high. And if I look to the concrete cover, the 60, because all was the bar, it was at concrete cover 60 millimeter, which this one, this green. So as you can see here, these bars, they were having 110 Celsius, like as TG, and you can see it from here. Approximately, we reached that in less than 1 hour, as you can see here. So all this is well above the TG. This is for one bar. This is GFRP bar type 1. I think this is the sand coated. As you can see, which is really very interesting results. This is the same thing, but for the other slab, the slab 2. And as you can see here, almost the same results, almost the same temperature, the same thing. And the most important result is both slab, you know, they did not fail after 3 hours. which is really 1 hour above the minimum required, which is 2 hours. One slab, you can see it here, it's failed, it's about 3 hours and 10 minutes. And we were really so happy, and a lot of people and engineers attended this testing, people from Ministry of Transportation of Ontario, Public Works of Canada, and many, many others. And as I told you, imagine if we got the failure in 1 hour or half an hour, as you know, it would be really catastrophic. But were really very, the behavior was very good, and it was done exactly by the lab, which is really recognized. It was done during the following the standard. And now, you know what we are doing now is tomorrow we'll be casting the next 2 slabs, and now the test will be repeated exactly the same thing as I show you, but it will be repeated with the concrete cover with only 40 millimeter. And I can tell you, if we can prove it, and moving from 60 to 40 millimeter, this is make FRP for parking garage extremely competitive, because for steel, they are specifying 70 millimeter. For corrosion issues and many other issues. And as you can see in the parking garage, sometimes if you can save 2 centimeter, 3 centimeter, it's huge on the cost. Sometimes only for removing the rock, as you know, from the foundation, like by excavating 5 centimeter more of rock, you know, the cost is huge. And also you can have the height. You can save a lot of. So the next result also will be extremely helpful, as you know, for expanding the use of FRP in parking garages and all the structures that the fire issue is a key issue. But at least even with the 60 millimeter, we were really very happy about that. So I can show you here some other. This is the failure of the slab. As you can see here, the failure. It was really by tensile failure of the bars. As you can see here. This is the in the middle of the span of the slab that it's fell. You can see the bar. It was they were having the color green, and now it's already black, as you can see, due to of course due to the fire. And it was by rupture of the bar. And it was about, as I told you, 3 hours and 10 minutes. So it was really extremely positive results, and hopefully, as I'm telling you, we'll be repeating for 40 minutes. Now I move to the external reinforcement very quickly before concluding to talk to you about this new standard dealing with the external reinforcement, and this cover mainly about the layup composite system. It's really being used for the hand layup. It's not yet used for pre-curved or FRP bar because we have the S807. So here, during the last few months, I did some testing mainly with 2 companies. This is showing with the, I think this is with MAPEI from Montreal. The original company is from Italy, and this is from Frissine from Ontario, and the origin company is from France. So I did for them a couple of testing according to this standard. And as you can see here, according to the S808 for the external reinforcement, this is really the main testing that we have for the environmental durability. We have the water resistance, we have salt water resistance, acid resistance, dry heat resistance, and freeze-thaw resistance. And here you have all the duration, the standard test method. And here you have the specified limit. It's mainly tensile capacity retention, as you have it here, greater or equal to 90%. This is for the Canadian. And if you look to the US, the ACI, we have the same testing with the same STM, the same conditioning, but in the percent retention in ACI, they are we can say less conservative. No, I don't know. Anyway, they are 85% compared to 90% in the Canadian. Yeah, this is showing some preparation of the specimen. I think. My colleague Emmanuel knows more than me in this field, so this is showing the FRP, the carbon sheet, and this is preparing the panels, as you can see here in the lab. We did with different layers, 1 layer, 2 layers, 3 layers, and so on. This is all the panels prepared, as you know, and for exposure in salt water, alkali, dry heat, water, freeze-thaw. Of course, if you are using this material in Middle East, so maybe there is no need to be qualified for freestyle. But here in Canada, of course, it's important to do that. So we have them all here, the specimen, and then we did the conditioning, and then we cut the specimen and we did the testing. This is what we, so you can see here the MTS machine that we used for testing the control and the conditioning specimen. And here, yeah, this is also we did about glass transition temperature by DSC, because we have also when we did when we complete the conditioning, because we have also limit on the temperature. It has to be, I think, 50 Celsius. And as you can see here, the control 62 and water 60, 58, 61, 54. What we found, dry heat, we found it really the most critical from this testing, the dry heat for both mechanical properties and also glass transition temperature. For the DSC, as you know, be very careful if you are doing it with DSC, because we in the standard we are specifying number with DSC, but also we have number with the DMA. And DMA, you have 3 approaches to determine the DSC. If you are looking to the chemical degradation, physical degradation, or mechanical degradation, you have different kind, but there is one kind which is close to the TG. So be careful about that. About the design code in Canada and in US, this is really how designing the bridge code and the building code, as I talked before. And of course, you have all the Canadian. I'm sorry here, this slide it was with animation. So I sent only the PDF copy, so we cannot see what is. But this is showing the ACI 1R, internal reinforcement, 2R, this is external reinforcement, 4R, this is test method, and 8R, this is I think for construction or masonry or something like. I think it's for masonry. And there is also H2 code. This is the new ACI 441R. It was recently published, 2015, for internal reinforcement. There is the most update was mainly about the serviceability for the deflection. We don't have at all now crack width calculation. We have on crack spacing an example. And we updated, of course, the literature review, and we about field application and so on. Of course, it's much improved than the previous one. Currently, we are also working with really a real code like as the ACI 318, which will be the internal reinforcement, and hopefully it will be published, as I'm telling you, as code as 318. By 2018, I am the chair of the task group dealing with the shear, and yeah, I think we have 3-4 task group, and we are really progressing very, very well this one. So here you can see, of course, when I will be talking about code and design code, I will be related mainly about durability. I will not be talking about the design. So the current code, we are addressing durability in many ways. First of all, through the material resistance and environmental reduction factors based on fiber type and exposure type. We know that carbon fiber is durable compared to glass, depending on the exposure condition and so on. Limitation on maximum stresses under service load. Glass, carbon, and aramid, they have different stress, maximum stress under service load. Limitation on crack width under service load. Limitation on maximum strength stress under sustained load. This is mainly for creep rupture and with GFRP. Concrete cover, as I say, with fire resistance. So maybe this one, I think we can make a huge progress. Creep rupture, as I say, fatigue, stress limit, and factor for long-term deflection, as I mentioned in my introduction. Some example of in the S6 code, this is the Canadian Highway Design Code. Resistance factor, we have 0.55 for GFRP. This means by using the characteristic strength, which is the mean minus 3 times the standard deviation, which means this is it's 90.99 percentile, which means one value over 1,000 specimen will be less than the characteristic. And with this value, we are using only 55%. This is how to show you how we are conservative, of course, by using this type of product. It could be maybe changed in the future. Stress on the service load, as I said before, 25. And crack width, we put it little bit bigger than the for steel bars, which is 0.3 millimeter. Because it's non-corrosive. Advances in FRP material durability, as I said before, we have the industry now is benefit from new materials, like as high performance resin with low diffusion and permeability, better performance consistent in new materials, fiber manufacturers. It's not really true with the basalt fibers now. It's still not consistent in the raw material and also in the variability of the material. This is really progress that should be made by the industry, mainly as I'm saying for the basalt bars. But for glass, carbon, I think this is all is well controlled. Continuous improvement on process and product quality control, as I said before, because now the industry has to, they have to do their qualification with the new standard, and they have to improve all their process and product quality. And now there are more manufacturers, so they have to be competitive and this. So it's, I think it's very good for the industry and to the end users to benefit from product of high quality and with reduced cost. Availability of statistical process control. This is, I visited a couple of companies, and all of them now, most of them are really using computer for controlling. You can see the technician will read from the computer and looking to the screen. If there is anything, he will have when it's everything is well working, it's all the lines are green, and when it's starting problems, it comes to yellow, and when it's have problem, it comes to red. So this is advising if there is anything, and this is all with the sensing, temperature, and many other things, properties being evaluated. Analytical method, as I said before, this is all I would recommend to you to use all this technique when you will be doing durability studies, and to understand very mainly about the, as I told you, about the phenomena being in the material, and also evaluating the performance of the material as you received it. And testing and development prediction models, this is important. And field studies, I think this is, we have to continue. Maybe I forgot to mention to you about the field durability studies. Now we have one currently being done in US. I was in Texas, Department of Transportation on May 21st, where I gave seminars for bridge engineers, and at that time they were taking course from one bridge where they used GFRP bars in the deck. It was built in 2000, so I think they have a couple of bridges that they were in which the GFRP bars they were used by the beginning of the 2000, and they took course, and the analysis will be made. I think I will be receiving some specimens to be tested. I know this project is being led by my colleague Tony Nani from University of Miami. So ensuring durability FRPs, this is key point. This is I'm showing here use of high performance resin system fully covered. This is really it's important topic. Otherwise, you can have some problems with the chemical degradation of the resin and more moisture absorption and so on. Minimize the formation of porosity, as I said before, and fiber impregnation also. Low moisture absorption. Select suitable sizing to ensure good bond. This is example basalt I'm mentioning here. And FRP bars repair should be manufactured. The standard have to be used. And code specified resistance and environmental factors and stress limit, of course, should be also used in your design. And here you have some concluding remarks. Of course, the corrosion resistance is without doubt the main motive and attraction to use FRP over the steel. And now it's becoming really like as conventional material. Now it's the material is being, of course, in from the beginning of the project, and the contractor has to prepare the tenders and submitting his tenders to the consulting engineering field and going through the whole selection. Mode of degradation, as explained before, are really well understood, but we need something really dealing with the synergetic effect, like combining load, environment, and temperature, and so on. Test method, I think we have what we need now for testing. And application in different, now we are getting FRP being applied really in various application. Now I'm working on some project dealing with the driven piles. I am planning to do some testing on the US East Coast for marine application and looking to the behavior of this material. Glass, we've proven it's really glass. FRP bars are durable in concrete. And the durability performance of FRP material is generally very good, based on the lab and also from field studies. And as I say, basalt, it still have some interface problem and needs to be resolved before this material will be used in the field and so on. Some research avenues that you can look to them, and maybe it could be very interesting. This is really in aging of in-service structure. This is really very good because it can be used, as you know, to prove the durability of the material of the material, and also it could be used, as you know, for establishing correlation based on the accelerating aging test. And this will be really extremely very good to develop some life predictive models, but based on the field testing from field and also accelerating aging test. And you have the other some other topic that I am mentioning here. So some suggested references, as you can see here. This is conferences that I organized myself in 98, 2000, 2007, 2016. I am planning to organize one by the next year in 2016, maybe here in Sherbrooke by next, anyway, it will be next summer. So if you are doing some research on durability, I will be glad to have you here in Sherbrooke. There is also this report, FDOT report, and some other report that also you can look at it of them. And I would like to thank you very much. I'm sorry.
So thank you very much, Brahim, for this very nice presentation. A lot of updating since last year. So the replay of this presentation will be available online, but maybe we have time for one or two questions for Professor Benmokrane. You can just input your question in the chat area, or if you want to speak directly to Brahim, you can also use your microphone. Okay, so Brahim, since
this is a good question because of course here we are talking about durability. So and the reason why I mentioned it, as you know, GFRP, because I was talking about internal reinforcement, and as I told you, because in terms of cost is extremely competitive. So carbon, of course, it's a very durable material. Let me maybe I have to read. There is one. Frey, he asked, you mentioned essentially GFRP. What about carbon or basalt? So I am responding to this question, okay? So as I say, I focused mainly on GFRP, like as internal reinforcement. The main reason is because when you are designing, even with GFRP, the stiffness is about, we can say, 30% of carbon bars. So you are expecting, as you know, most of the design is governed by the serviceability. So you can expect by using carbon, you will have 3 times less quantity of material to be used in one concrete member. But as you know, the cost of carbon is almost 6, 7, 8 times greater than GFRP. So GFRP is still really extremely economic and competitive compared to. This is why I talked about that. But of course, carbon is durable, but it's limited mainly for pre-stressing. It's because GFRP we can use it, but with very low pre-stress load. but carbon bars and carbon rods, they are being used for pre-stressing. In couple of bridges, they were using in longitudinal direction over piers when we have a longitudinal negative moment over pier, it could be a huge moment. Even with GFRP, you have to use really larger size of bars. Even sometimes with 25 millimeter or 35 millimeter, the spacing would be so close. So we can use carbon in cases. Basalt, really not yet. As I mentioned before, I did some application, some pilot project. I think it will be good material from perspective of basalt fibers, but we need really to look about the interface, and I can see it really good candidate. Mainly if we can. I'm not seeing it like as competitive to the glass, because basalt, I'm looking at it, I think for pre-stressing from a perspective it would be excellent, because we can have many applications now. Even if I mentioned it with carbon is being used for pre-stressing, but it's still some authorities, they have really problem when they are during the operation of pre-stressing, because carbon is still very brittle material, and any sometimes small deviation or inclination, it will bring the material to break. And I know there is one plant in Manitoba, Lafarge. They have precast pre-stressed slabs, mainly for parking garages, and I can tell you they are losing between 15 to 20% of the material carbon during the pressing. So basalt, I think, to be a very good candidate, because it has elongation, it's higher, it's almost the same as glass or even higher than glass. I think it will be good candidate. And also there are some engineers, some end users, they are not still confident to use GFRP. The word is like this. So maybe when we are talking to them with basalt, so they are a little bit more open. So maybe they can use it so in this way anyway.
Okay.
But it's mainly, the GFRP is mainly due to the cost and its proven durability now. In conclusion, durability of GFRP is enough and should not be. No, I don't want to say. Yeah, Khalid is saying in conclusion, durability of GFRP is enough and should not be improved. No, I'm not saying that. I think any material that we can make it better in terms of durability, we can maybe have better design. We can optimize the design. We can use maybe less material. Maybe we can increase the stress on the service load. We can make really design better. So I think yes, if we can improve it, of course, and I'm encouraging the industry to improve it as much as they can. Yes.
Okay. Brahim, I have one question. Based on your own experience, you have a lot of data coming from your lab and the field about accelerated aging. Are you confident now enough in accelerated testing to qualify new material, or do you think we need more field application to check about the real durability of material?
No, I think from our point of view, I think of course we need really to continue to work on both sides. From our point of view, the lab testing and mainly for the qualification, even I know it's the conditioning that we are using is extremely severe, but I think it's from our point of view we have to keep it, because by this way we'll make sure that no good product will be using in the field. You understand me? And I know now the industry what they are doing. It's at least they are making their product, improving their process, choosing their raw material, their constituent, at least to match or even to be better than what we have in the standard. And all the standard, because we have it like as quick test. Of course, we have to keep it with the lab, and we have to do it as the way that we are doing. It could be maybe in 5, 10, 20 years, maybe the things will change. We'll see at the time. And we'll continue to do field testing. But the field testing, what I would like to know from that is really showing if there is any degradation or anything that we can see it, at least as you know, to make comparison for what we are doing in the lab. It's mainly to have the prediction. So I think I will continue on both, but of course I will keep all the testing in the lab. It has to be kept. No doubt about that. No doubt. Yeah.
So, is there any additional comment or questions? I think you can be free also to ask for Brahim Benmokrane some papers or so on by email. This webinar will be available maybe in 1 or 2 hours on the IIFC website in replay. It takes about 1 to 2 hours to record all this talk. So thanks again, Brahim, for these very nice presentations. Last questions? No?
Thank you very much for attending this webinar, and thank you, Emmanuel, for organizing all the things. And thank you very much.
It's my pleasure. So thanks for all of you to be here in the evening or later, or maybe earlier, depending on where you are in the world. And have a nice day. Bye.
Thank you. Bye bye. Thank you.
And Brahim.
So it's fine. So I will.
Okay, so bye. I will close the session. And Brahim, if you have more time, we can discuss about it on Skype. I have a few minutes.
I can keep it? Okay, yeah.
We may move to Skype. It's
I have to touch something or not?
I think, no, it's okay. We'll move to Skype.
Okay.
Okay.
So I have to close it and go to Skype?
Yes.
Okay.
It's okay. Perfect.
You are currently the only person in this conference. You are currently the only person in this conference.